Good afternoon and welcome to our session on embodied carbon and structure. On behalf of the Boston Society of Architecture, thank you for joining the third session of Embodied Carbon 101, the BSA's 12-part program series taking place this summer. Following up on the Embodied Carbon in Buildings conference that the BSA presented in 2019, the series will bring you embodied carbon programming almost every Monday, providing you foundational knowledge in different impact areas, and giving you tools and takeaways that you can apply to your everyday work. I'm Suni Dillard, an associate at HMFH Architects in Cambridge, a Cambridge-based Massachusetts architecture firm. I'm delighted to be joined today by Gregory, a research scientist in the Department of Civil and Environmental Engineering at MIT and the executive director of the Concrete Sustainability Hub. Michael Gryniuk, an associate at the Boston-based structural engineering firm LeMessurier, and a lead in the Structural Engineering Institute's SE 2050 commitment. And Chris O'Hara, a founding principal of Studio NYL, a Colorado-based structural engineering and facade design studio with offices in Boston and Minneapolis. Chris and Studio NYL are members of the Carbon Leadership Forum and signatories to the Structural Engineers 2050 Challenge and AIA's 2030 Challenge. I want to take a moment to thank our sponsors for this series: Arc Woods and Services, Goody Clancy, Huber Engineered Woods, Kingspan, Select Building Products, and Thought Forum. We're grateful for your support. And thanks to our partners, the Associated General Contractors in Massachusetts, Built Environment Plus, and the Structural Engineering Institute. And I'd also like to recognize that this program series is supported by the Carbon Leadership Forum and its local knowledge community, CLF Boston, which we invite you to join if you're interested. Before we dive in, a couple of notes about this program. One HSW Learning Unit is available for those who are eligible. We will share a link to a Google form in the chat box. If you want continuing education credit, please add your name, email address, and AIA number there. If you're not an AIA member but want a certificate, please enter your name and email address. We're recording this session and it will be posted to the BSA website, architects.org, later this week for your access. We ask that you share any questions using the Q&A function. Our presenters will stick around for a few minutes, but they don't have a ton of time. So if there are any additional questions that we don't address, we'll be able to address them or to help inform future programming, including the remaining sessions in the series. With that, let's begin. I want to spend a few moments addressing the importance of focusing on embodied carbon, specifically within structural materials and systems. Based on a study by Thornton Tomasetti that measured the embodied carbon of 600 buildings, structure made up approximately 55% of a new building's overall embodied carbon. As you can see, for commercial buildings, 47% of that was in the floor, 16% in the walls, 12% in the framing, and 6% from the columns. This highlights the importance of engaging with engineers to review structural solutions for all projects. Today, we're here to help with some basic information. For simplicity, consider 3 high-impact materials: wood, concrete, and steel. As design professionals, we often get stuck dealing with code, program, material availability, durability, aesthetics, etc. However, collectively, we can push the boundary of our goals while meeting the common objective of carbon reduction. What questions should we be asking as designers, engineers, owners, and builders? We understand that no material can be swapped one for one, but this does not excuse us from building more appropriately and addressing cost and carbon holistically. I'd like to share some ways that we can improve upon the basic processes that contribute to the environmental impacts of these 3 materials. If we understand the weaknesses of each, we might be able to understand how to use them more effectively and efficiently. Concrete is made up of water, cement, and aggregate, and air. Reducing the amount of cement in the mixture is the most effective way to reduce the carbon footprint of concrete. Tackling this early in the process is critical in meeting project expectations and timelines. Steel. There are quite a few things that can be done to reduce the embodied carbon impact of steel, but the best way is to use steel from electric arc furnaces that are powered with renewable sources. In addition to minimizing the impact of fabrication energy, these facilities are more likely to have the highest recycled content in their raw material. Wood can be the most ideal structural system because its raw material sequesters carbon, but care must be taken into its growth, harvest, and replenishment. Bad practices lead to inequalities in our socioeconomic system while damaging the forest ecosystem. Choosing sustainably managed forests is the best way to reduce impacts from timber harvesting. Today, you'll hear from 3 engineers, as I mentioned earlier, that are going to provide guidance on how to make decisions and what boundaries we can push with our structural systems with carbon reduction as our goal. They'll be addressing questions of scale, role of planning, and I'd like you all to remember that change happens with collaboration. With that, I'm going to hand it over to Jeremy. And you're good, Jeremy, if you want to share now.
Excellent. Thanks very much, Suni. I really appreciate the introduction, and I'll go ahead and get started. I'm delighted to be part of this session on embodied carbon and structure. As mentioned, I'm at MIT and the Concrete Sustainability Hub, and today, so my focus is going to be on lowering the embodied carbon of concrete. And, you know, I think what I want to start out with some framing discussion is that, you know, concrete, as you probably heard, is the most used building material in the world, and it is for good reason. It has many different properties that lead it to be used so often. It's economical, meaning it's relatively inexpensive. It's versatile. It can be used in many different ways. It's durable. It lasts for a long time. It's constructible. It can be constructed in many different ways. It's available using resources that are found all over the world. And it can be made very beautiful as well. And I think one of the exciting things about it is that there's a lot of innovation that's happening right now that's constantly changing all of these different attributes. But I think there's a misperception about concrete that it's often called a high impact material. And actually, when you dive into some of the numbers, it's actually a low impact material. And the reason that you can see that on this chart right here is that if we look at the embodied carbon in all these different materials, and this is also showing embodied energy, which is just the amount of energy required to produce them. And note that this is a log scale. So this is 0.1, this is 1, and that's 10, showing all these different materials. You can see that concrete's in the lower left right there. And that's because on a per unit weight basis, you know, it's pretty low impact because it's mostly just made up of rocks and sand that we dig out of the earth. So when we talk about the impacts of concrete, certainly on a per unit weight basis, it's not high impact, but we use so much of it. And because it is the most used material in the world, that's why we're talking about it. And it's often the most used in many of our buildings. So the other thing to keep in mind is that, you know, concrete is really critical to meeting different societal goals. There was a study that was recently done that showed that the importance of infrastructure to meeting the United Nations Sustainable Development Goals, and concrete's usually a big part of that. If we're going to address the affordable housing shortage, we're going to need more housing, and concrete's going to be a part of that, regardless of what the structure is made out of. You know, and lastly, if we're going to decrease costs and save lives associated with natural disasters, we're going to need to build more resilient, and concrete's going to be a part of that as well. So I think our use of concrete really represents a tension. On the one hand, we need development to help us achieve our societal goals, but obviously we want that to be sustainable as well. So how do we try to accomplish both of those things? First of all, I want to start out just making sure we're on the same page. You know, that concrete is a mixture, and it's made up of all these different things: coarse aggregates like gravel, fine aggregates like sand, a binder that I'll get into, it's often cement, water, and then sometimes chemical admixtures that can affect the properties. And we combine these things, frankly, in almost infinite different ways to meet many different properties. Of course, strength is one thing that we talk about, but early strength, while it's being constructed, is often as important. So there are other things like stiffness, density, constructibility, and durability. So it can actually be kind of complicated, the way in which we combine all these things to meet these objectives. The other key definitional point is about what we mean by this binder, and there are many different types. The most common one you hear about is cement or ordinary Portland cement, but there are also natural pozzolans or calcium all over the world in some locations. And then there are also different waste materials that we can use as well. Fly ash from coal-fired power production, granulated slag, which comes from iron, production, and increasingly also an option is to grind up post-consumer glass and use that as well. The key thing, though, is these are not all replaceable as a one-to-one alternative. You know, the composition of them, the availability, and also the performance in the concrete can really vary significantly. When it comes to environmental impact, a key thing to think about is what concrete is made up by mass. And as you can see, it's mostly these aggregates by mass. You know, a little, about 10 to 15% is going to be cement, and then there's some water. But when we look at the breakdown of the greenhouse gas emissions, you can see it's almost entirely driven by cement. And so that's why we often will focus on that. And we need to differentiate what's the driver by weight, and then instead, what's the driver of the environmental impact. Now, when it comes to lowering concrete's environmental impact, and also cements, because you can see that's such a big driver, there are many different solutions that are available today to do this. And I won't be able to get into all of them because of the time constraints, but just to give you at a high level, there are several different things that we can do in the ways that we produce the cement, whether it be about the fuels that are used or the energy efficiency. But there are also some more advanced techniques that can be used related to carbon capture, or also either carbon capture at the cement plant or actually making products using captured carbon. Similarly, on the concrete side, you know, I mentioned how cement is a big driver of that. So if we can replace it, there are some lower carbon cements or supplementary cementitious materials that can be used. But also, I'm going to talk a bit about specifications and the role that they play. If we can optimize our mixtures by changing specifications to be more performance-based, that can help. There also are some technologies that are available where we can use captured carbon in the production of concrete and aggregates, and those are things that can lower environmental impact. Now, the key thing to keep in mind, there are a couple different barriers to adopting these technologies, and they're really risk aversion and costs, and I really put them in that order. Cost can be a factor, and obviously is, but most of the time it's basically this aversion to wanting to try something new. And of course, when we're using concrete, the stakes are almost always high, right? Whether it's buildings or bridges or what have you. And so I very much understand that risk aversion. But on the other hand, if we're going to really have an impact on something like climate change, we're going to have to do something different. So what I wanted to introduce to you is something that, a process that Mike Gryniuk, who you're going to hear from next, and we kind of came up with about how you might implement a low carbon concrete in a project. And this can also apply to just about any different material, but we'll use some language here that's specific to concrete. The first thing is making sure to engage the architect, engineer, contractor, and ready-mix concrete supplier, and also the owner to define goals based on a reasonable baseline. The next step is to review the existing specifications to understand current constraints. Step 3 is determine what are available solutions to lower the concrete impact and their associated cost and performance implications associated with those solutions. Select the best solution by evaluating what are trade-offs among performance, environmental impact, and cost for those things. Revise your specifications if possible, and then implement it. So it seems maybe pretty straightforward, but there are really some significant challenges. Establishing a reasonable baseline can be difficult, and determining what are the cost and environmental impacts associated with those different solutions. So that's maybe a whole other webinar we could get into on that. But you notice that there is a role that specifications really play, whether it's what's going on with existing specifications or changing specifications. And it's because of that I wanted to mention that a lot of specifications are very prescriptive, meaning that they get into a lot of details on like exactly what has to be in the concrete, and they end up limiting opportunities to reduce the environmental impact. For example, a lot of specifications will restrict the amount of supplementary cementitious materials that can be used, have a maximum water cement ratio or minimum cementitious content, and those are all things that end up increasing the environmental impact. So if we can review those and then change them, it has a big opportunity to do that. And so shifting to more what we call performance-based specifications is one of the best and most straightforward ways that we can spur innovation in low impact concrete. And basically what we want to do is to optimize mixtures to meet those performance specifications within maybe some targets for cost and environmental impact. But in order to do that, because it's that change that I mentioned, you really have to have collaboration among those key stakeholders I mentioned, the architects, engineers, contractors, ready-mix suppliers, and owners, so that we can share in the planning and then also the risk mitigation as well. So just to wrap up, what are some of the immediate actions that can be taken to lower this? First of all, there's a lot of great resources out there. One, you've maybe already heard about this SE 2050 that Mike's leading up, and we put together some resources on that website. The National Ready Mix Concrete Association has been talking about the role of performance-based specifications in terms of lowering environmental impacts. That's a great resource as well. And the other thing I think is, even though that whole the process that I mentioned seems kind of overwhelming, just get it started. Engage in a discussion with these folks about it, and then review some of those existing specifications to understand what opportunities you have, and then work with the project team to find a solution. Even if you don't have all the data we mentioned right away, I still think just by starting that discussion with the team, we'll be able to make some progress. So with that, that's our contact information in case you want to follow up. And as Suni said, I'd be glad to answer questions as well at the end.
I'm up, right, Suni?
You're up.
Okay, well, thank you, Jeremy. And I am also very excited to be here to talk about the embodied carbon of structural steel systems. So like Suni said, I'm an associate at LeMessurier here in Boston, and I'm also chairing the SE 2050 committee right now. So just to get your mind into steel.
Mike, will you share your slides real quick?
I'm sorry?
We can't see your slides. There you go.
Okay, see it now?
Yep, now you're good.
Sorry about that. So to get your mind into structural steel, I just want to quickly talk about this picture here. So structural steel systems are nothing more than large erector sets, and the pieces are generally rolled or shaped at a mill, and those are then shipped to a fabrication plant where all these bolts and plates, and they're punched to receive bolts, and all sorts of stuff are added to them. Then they're put on a truck and they're shipped to the site. And so the picture on the right is just something in construction. You can see there's a crane that's holding a bunch of steel, and there's people walking around the frame, installing the material, and there's a variety of different things going on here that I won't get into in too much detail. But bringing your attention to the picture in the middle, this is what's called a composite steel system. So there are galvanized steel decking elements that will span between the structural steel beams. Those are then welded to the steel frame, and then when the concrete is placed on top of that, also called a concrete topping, it becomes composite with the steel through the headed shear studs that you see in the picture there. So that's the mechanism to prevent slip between the concrete and the steel. And then on the left is just a common brace frame system that would be used to resist lateral loads and provide overall stability. So when we're talking about structural steel framing systems, there's a lot of different parts and pieces that would come into play when we talk about the embodied carbon impacts. So on the right is just a typical framing scheme. Within that is obviously the structural steel members, but then there are all the connection materials between the members. There are the headed shear connectors, the metal decking that I spoke about, the topping, and then whatever is reinforcing that topping. And then of course, surface treatment like painting and priming, and a big one is steel fireproofing the steel, which has a significant impact. And then of course the construction and all of the end-of-life sequences that you've already talked about in the last session. And I just want to mention that somewhere between 80 and 90% of the embodied carbon is related to the product stage, the A1 to A3, which you learned about last week. So here are the answers to the quiz. How do you reduce the embodied carbon of structural systems? Well, first and foremost, use less material. Okay, so that's fairly obvious. One that may be less obvious is using fewer pieces, because using fewer pieces is less fabrication, it's less shipping, it's less crane time, it's less crane picks. Then the tricky one for steel is specifying better steel. Okay, and we'll get into that in a second. And then, of course, all the materials that are attached to the steel frame, like the concrete, also has a significant impact, and we've got to find ways to reduce the impacts of those materials, and in particular the concrete that Jeremy just spoke about. And then there's being smart about the embodied carbon budget of the overall frame, and finding ways to shift the burden of the embodied carbon in different areas that you can control. And I'll get into that in a second. And then, of course, as designers, one of the biggest roles we have is sending market signals and demanding less impactful materials and ways to build. And it really, steel is all structural systems is a combination of the design and the product specifications. But I think when it comes to steel and the interface with the structural engineer and the steel fabricator, it's really, really important, not just the material itself. So getting into the material, won't spend too much time on the science and the chemistry of it, but it's mostly iron, and it's got a carbon content between 0.2 and 2%, and a lot of other elements. The vast majority of the impacts of structural steel come from what's called the furnace stage, and there are two primary furnaces, the basic oxygen furnace and the electric arc furnace. And without getting into too much detail, the main difference between the basic oxygen furnace and an electric arc furnace is the BOF is using a lower volume of scrap steel, and it's using a much higher volume of virgin materials and breaking down iron ore and sort of melting coal, so it takes a tremendous amount of energy. And then it's called a basic oxygen furnace because on the final stage, the oxygen blows over the pig iron and then you have steel. Conversely, the EAF is using almost exclusively scrap steel, 95 to 97%. The furnace melts it at 3,000 degrees, and there's a few additional elements added to get the chemistry right. And then when you sum that all together, the embodied carbon impacts are about less than half of a BOF. Now, the narrative for a while now has been to always specify EAFs, right? That's the easiest way to reduce the structural steel. And that is generally true, but you've got to be very careful about it. So if you take a step back, the North American steel production in 2018, the vast majority of steel from the US for US building is North American sourced, and already 70% of it is EAF. The challenge is that that's actually the majority of that is from one company. Okay, I'm not going to get into what company that is. You can probably figure that out, but it is one company. So when you talk, and they did it not for environmental reasons, but more because it's a smarter business model. Okay, and obviously the unintended consequences is that there's reduced embodied carbon impacts. So you've got to be very careful about specifying the furnace type. And you can see here the BOFs that are shown on the screen. Even some of those are starting to become offline, but I can tell you that right now, one of the other big producers of steel has just started their first EAF in Arkansas. Okay, so just to give you a sense of where the market is. So before we get into the specifying of the materials, just want to take a quick step back and talk about the different impacts of the three main pieces that the American Institute of Steel Construction publishes. These are the industry-wide EPDs, so A1 to A3. And so for a standard hot rolled section like a Y flange, you're at about a ton of CO2 per ton of steel produced. And then, there's a range steel plate, and then all the way up to the HSS members that are almost 2 times that of a hot rolled structural shape. These numbers are based on a very small number of big producers, and the producers contributed data, but not necessarily EPDs, and that will come into play when you start considering doing facility or product specific EPDs. And the question is, are these conservative numbers? Well, frankly, it depends who you ask. If you ask some suppliers, they'll say these numbers are very conservative and others will not. So steel is very tricky because it's unlike concrete, which is very local. Steel is a commodity, and it's a highly competitive product, and I'll just leave it at that. So there's 2 options for specifying steel, right? The number one option that we hear about is specifying EAS for all your steel. So in general, yes, that'll return a lower GWP. And the example of the spec is basically saying that all the steel has to come from electric arc furnaces. The challenge, of course, is that it may be restrictive on the supply chain of things. And also it may favor one material supplier. And also, let's not forget that not all EAFs are treated equally. I mean, you really have to understand the electricity source of all your EAFs to be confident that the EAF will produce a lower GWP or the GWP that you're looking for. Option 2, this is one that we've been playing around with, is actually specifying GWP limits or embodied carbon limits on the steel. And so that really is going to be a derivative of the industry-wide averages that are published. We think this will give more freedom to the construction manager to procure the material. And it may be an easier conversation to talk about embodied carbon or global warming potential than it is to talk about the furnace type. And it's sort of in line with a stronger market signal, because right now the discussions are all about global warming potential. In this particular case, this was the embodied carbon values were reduced by 25%, and then the requirement was 75% of the product tonnage has to meet these numbers. So getting into the member types, member type does matter. So here's an equivalent wide flange and a plate girder, okay? Similar depth, similar stiffness. The challenge is that the wide flange member is less weight, but it's, I think I have those numbers wrong, but, oh, I'm sorry, yes, the plate girder is a lower tonnage, but the global warming potential of that plate girder is higher simply because you're using plate material, okay? Another member that to be wary of is that although HSS members are incredibly efficient in axial forces, and they're often used as bracing members, they have a pretty high GWP. So here's a basic brace frame example showing comparing a wide flange 8 to an HSS 6, and it's the same story where the HSS member is much lighter, but it has a much higher global warming potential. And another option for structural steel, about 5 years ago, A913 or grade 65 and 70 has become readily available for W14s. The normal steel strength or steel grade is 50, but 65 and 70 has been really picked up a lot in the last few years for W14 jumbo sections. So your overall tonnage will come down, and they say, depending on who you talk to, the global warming potential is lower anyways. So it's sort of a double positive where you have a lower tonnage and a lower embodied carbon. But you do have to be careful about serviceability because the stiffness of steel doesn't change regardless of the grade of steel. So quickly getting through the structural steel systems, there on the right is a list of a whole lot of things you can start to consider when you talk about structural steel systems. I'm going to focus on 3 very quickly and talk about maximizing the deck spans, being careful with lightweight concrete, eliminating transfers, and continuous beams. So here's an example of a 3-span versus 2-span deck condition. When you look at the quantities, the number of steel pieces drops, structural steel drops, shear connectors, angles, bolts, all that goes down. Global warming potential using a commercially available software is about the same, but that software is not including the reduction of all the quantities I just talked about. Another issue is you want to be very careful with lightweight concrete. We often see structural steel frames with 3,000 PSI lightweight concrete instead of 3,000 normal weight. But the global warming potential of lightweight concrete is about 2x that of the normal. So when you do a life cycle assessment, you get a global warming potential that's almost 2x that of the normal weight concrete system. Now, anybody here, any structural engineers on the call will start asking me questions about the seismic mass and the supporting frame mass, and that's all correct. But I would say that the small uptick in tonnage may not nearly come in the associated embodied carbon wouldn't match that of the impact of the lightweight concrete. Transfers, here's a basic example where we eliminated 12 tons of steel by removing a transfer girder. Here's one, even in short girders, one idea is cranked or sloping columns where you can pull out a couple of tons of steel. And yes, you have to consider out of plane forces, but they're relatively small if it's a short slope. Continuous beams on the roof is one that our industry has gotten away from. So if you go to continuous members on the roof, you could potentially save 48%, 4 to 8% in your roof structural steel. So just wrapping things up, getting, going back to the same, using less material, using fewer pieces, specifying the better steel, reviewing the composite material impacts, and sending the market signals is really key for the structural steel. And then in terms of getting people involved, it's really important to have early collaborative engagement, tracking of the material quantities and the embodied carbon throughout the project. It's going to require more conversations. And a big one is making sure that you're maintaining momentum. Momentum in the embodied carbon world tends to ebb and flow throughout the project, and it's important to keep it on the radar. And then I think it's also important to share all the lessons learned. So thank you very much. I can hand that over now. Let's see here.
Hello, I'm Chris O'Hara. Sorry for the slight delay there as I was trying to get unmuted. Hopefully everybody can see my screen. So I'll be covering the timber portion, which kind of lets me be a little bit of a hero of picking the material that can actually go carbon positive. So as we're thinking about why timber, first of all, in its life prior to becoming lumber, it is a carbon absorbing material and it releases oxygen. So for much of the life of this wood before it becomes lumber, it is actually helping the environment. The challenge then starts to become what happens at the end of life for the wood. So by harvesting the wood prior to decomposition or burning, we're actually keeping that carbon sequestered within the lumber. The managed forests are able to maintain a cycle so that we're always trying to keep that wood from hitting the end of its life and therefore releasing its sequestered carbon. And then the lower energy used to produce construction materials, the relative amount of energy it takes to take a log and turn it into lumber is much lower than some of the other structural materials you're currently seeing. One of the challenges often is where our species in the world live other than humans. And this heat map you see here, where red is the most dense number of species, blue being the least, you're starting to see that most of the variety of species on Earth generally live in the tropics. And as you start to transition that to where various trees are existing, there is a wide variety, and obviously the tropics have quite a few of them as well, but they tend to be hardwoods, where most of our structural lumber are actually softwoods. So as you start looking at all these different areas of where the lumber is coming from, when we talk about structural lumber, most of it's coming from these green and blue areas. So obviously well outside the tropical areas. And then you start looking at maps of managed versus unmanaged forests. Quite a bit of Canada and Northern Europe are predominantly managed and certified forests. The United States, we're not doing quite as well, and we'll get into that in a little bit, as well as other parts of the world aren't doing quite as well. Our structural timber in the United States, most of it is domestic, about a third of it's imported, and almost all of that is coming from Canada. So those are generally coming from certified forests, and there's a little bit of other wood coming from other places. This is not counting finishes such as some of the hardwoods and things like that that may be coming from more areas. As we start talking about managed forests, we're generally talking about certification. The flagship for this is the FSC, or Forest Stewardship Council. This is definitely the more rigorous of the two primary ones you're seeing, which is the other being SFI, Sustainable Forest Initiative. And there are a variety of differences between them. Most of them have to do with use of pesticides and the way the forests are managed. But from an embodied carbon standpoint, the thing that's most critical is often their rules against clear cutting and some of those elements that come into the management of the forest. Many of the other items, although they're very important from an environmental standpoint, aren't affecting us nearly as much. So as we're specifying wood, FSC is definitely where we want to be going if we can. You will find that the availability of wood in FSC may vary depending on what you're looking at, whereas standard sawn lumber and say engineered lumber like TJIs or I-joists might be very hard to find from an FSC plant. Like, for example, Weyerhaeuser, one of our largest suppliers, is only SFI certified, whereas some of the more mass timber elements, generally getting FSC is a lot easier. So what are we getting from managed forests? We're getting protected areas that conserve biodiversity. The most important thing, I think, is the management plans. In other words, how are they harvesting the wood? How are they dealing with their waste? In other words, many lumber yards, when they get waste wood, they end up just burning it, which means we're taking all that sequestered carbon and just putting it right back into the atmosphere, which is not what we want. How they're dealing with their replanting process, and how their timing is. For example, there are a lot of forests that are SFI certified that are harvesting, say, Douglas fir at like 40 years, where really you want to allow that to go more 70 to 80 years prior to harvesting. So that kind of management is critical when you're considering how much of the carbon is being sequestered by the wood and what we're actually getting in our LCAs. Counter to that, you start seeing comments like specifying faster growing species because they're storing carbon faster. The challenge is oftentimes people are trying to harvest sooner than they probably should. So there is a balance there. And then obviously using faster growing species like, say, a bamboo, you're increasing that cycle of materials. One of the challenges of people who are harvesting the wood too soon, the wood is not going to be as strong, and therefore it's not going to get you. So as we start getting into the different material types within lumber, sawn lumber, it does have a lower embodied carbon than most engineered products, mainly due to how you turn it into a usable product. It's cheaper, easier to use. It's what you're seeing in most manufactured housing and lower rise multifamily housing. The cons, the bad sides, is nowhere near as strong as engineered material, has poor dimensional stability. Those of you who've been to Home Depot have probably seen that quite well. And then the other challenges as structures get bigger, larger pieces of lumber take larger trees to make. Whereas when you start getting an engineered lumber, it could be made considerably easier. And then the durability and lifespan of this timber. When we're thinking about the embodied carbon of buildings in a longer term, if the life of the building is significantly less than another construction type, that other construction type needs to be considered overall. Engineered lumber, it's got a much higher strength to volume ratio. So even though it may take a little bit more carbon or energy to make it, we're using less material. Using less material is obviously going to be helpful. It's more dimensionally stable, tends to be straighter, flatter, things of that nature. And it can be made from smaller diameter trees or portions of trees. The cons, like I said, it's more energy to produce, which means it's got more embodied carbon and it's going to cost a bit more. So when we start thinking about embodied carbon, as Michael was alluding to, there's two parts of the equation. There's the material quantity and the embodied carbon coefficient. So less material should be less embodied carbon, as well as what you can get from just choosing material that has less embodied carbon. With wood, it gets a little bit tricky, and this is where you really got to be careful with greenwashing. Whereas this chart from Crosslam is showing a negative global warming potential. Now, the key element of this is it's cradle to gate, not cradle to cradle, as you're starting to see. So what's missing from this number, even though it's negative, it's missing transportation. It's missing construction or on-site waste, cost and energy to erect it. And then the most importantly is the end of life release of the carbon sequestration. So how is this material going to hit the end of its life? Any waste product on that, how is that being recycled or is it being burned? Things of that nature have to come into play when you're looking at this. So we have to be very careful when we get into our LCAs. So when you talk about using advanced framing as an option, this is a way of reducing the amount of material used. And if you're talking about something like this with steel or concrete, any engineer who didn't design this way would basically be fired. Essentially, advanced framing is talking about getting materials to stack, for example, the truss or the joist to stack directly over the wood stud that's supporting it, and eliminating the need for a double top plate, only using headers where we need them. So if it's parallel to the span of the floor joists or roof trusses, you really don't need a header for that window. Things like that are inherently wasteful of material, but the reason you're seeing it so much in this type of construction is it's a lot less labor. It doesn't require thought and layout in the field, but it is a horrible waste of material. So what may be just the minimum requirement for materials like steel and concrete or even masonry. In wood, just to reduce labor costs, we're wasting material left and right. You can kind of see just the density of material in each of these two graphics. Another way is to maximize the efficiency of a material by using depth as a friend. And I don't want to overwhelm people with equations, but what you're starting to see here is length squared in the bending moment. That's what's covering our stress on materials first. So the longer a material gets, it's getting exponentially worse in terms of the amount of bending. The transitive of that is the deeper the structural member gets, it's getting exponentially better at resisting that bending. So deeper structures are going to be more efficient for bending. So by not having solid material top to bottom and creating trusses, you're able to resist that load much more efficiently. And this is, you know, for good or bad, the most efficient way to really build a roof on a house or a small multifamily project in terms of both cost and material efficiency. What about bigger buildings? I mean, this advanced framing and use of trusses is all great, but you know, when we're talking about doubling the amount of square footage of buildings in the next 40 years, 1 to 4 stories ain't going to cut it. So you know, we have to start thinking about how do we deal with our long span structures in wood? How do we deal with more dense structures that we're going to see in our urban environments? So you're starting to look at using structure more elegantly, which enables us to use less material, transfer the forces more efficiently. And then, of course, the big buzzword in the industry right now of mass timber. So elegant structures, that's where, you know, people like us get to have a lot of fun. The structure starts to be really demonstrative of what it's trying to do. So with arches, we start with large span to depth ratios, using the geometry to more efficiently move the force to where it needs to go. And there's just a variety of those, always thinking about any unbalanced loads that'll come out of it through the arching effect. And you always hear that term tied arch and trying to create a closed loop system. Or what about more three-dimensional forms and long span structures using things like grid shells and lamellas, where we're able to actually use relatively small pieces of timber to span exceptional amounts of difference using geometry as our friend. Oftentimes we're developing these through parametric studies using Grasshopper linked to our Rhino and analytical models. Also ways of dealing with elegant structures is try to reduce that span of bending by tricking the horizontal timber member into thinking its span is less, like in the sense of a king post that you're seeing in this image. You're tricking the member into thinking its span is half as much while using the depth of the structure to create a push-pull effect in that there's compression up in the timber member while there's tension down in the steel rod, and playing to the strengths of the materials we've got where the steel is exceptionally efficient when only subjected to tension and buckling isn't an issue, whereas the timber member being braced by the roofing or flooring is able to be more efficient. So you're seeing here are the two diagrams. Everything in red is in compression, everything in green is in tension, and you're seeing one post being a king post, 2 posts being a queen post, and then there's a variety of tensile structures we can develop, adding more and more posts as we try to keep these closed loop systems to balance the forces. But as we start getting into taller structures, the solution is going to lead more to mass timber. There's a variety of types of mass timber. When you talk about the flooring, which as you saw in that Thornton Tomasetti image Suni showed earlier, there's most of our embodied carbons listed there. So here you see the wide variety. When we talk about mass timber, most people are thinking about cross-laminated timber, but there's also nail laminated, glue laminated. Not shown here is dowel laminated. Whenever you hear the term laminated in these cases, it really just means getting them to work together. Obviously, nails is a relatively low-tech method, as is the dowels, whereas the glues are relying on adhesives. One of the things that are becoming a little bit trickier in certain jurisdictions due to some of the failures at Oregon State University not too long ago, there's a little bit of hesitancy in some building departments in accepting glue laminated elements for these. The reality is those failures are more related to quality control on those and has been proven not to be directly related to the material type, assuming that proper quality control is taken. One of the other things you're starting to see quite often on projects specified with mass timber is substituting in tongue and groove decking. Oftentimes this can be a much stronger material. relative to its depth, but it's going to, similar to what we talked about earlier, is it's going to deflect a lot more. But when Michael was talking about using stronger steel, using stronger wood is also going to result in you still have to deal with the deflection and serviceability needs. The other things you were starting to see is use of timber, concrete composites, but once again, we're bringing in some concrete into the equation. And as much as we do this quite often for acoustics, having those masses directly touching doesn't actually help us with the acoustics. We need them to be separated by some kind of acoustomat or something that separates these two masses. So here's just a quick understanding of some of the difference between them. And the big thing with cross-laminated timber that's unique is since they're constantly rotating the plies as you go through it, where the ones that are longitudinal with your span are at the very top and very bottom, you're able to get some two-way action. It's not as strong in the direction that's not parallel to the top and bottom elements, but you're able to get some side cantilevers and things like that that the other products aren't really able to do quite as well. And that's one of the bigger differences. You're also going to see there's a slightly lower capacity depending on the different types you're using for these flooring. This will be more for the handouts, but some of the positives of cross-laminated timber really obviously have to do with this carbon sequestration and embodied carbon. But you're able to actually get relatively shallow structural depths for the spans that it's doing, because it is just a significant amount of mass going support to support. But it really requires a lot of coordination. When you're looking at CLT, try to stay within the 3-ply and the 5-ply elements. All the projects we've done that are moving into construction are really all 5-ply at this point, just because of the cost per square foot and trying to get them to work within the cost and the modules that we had to work with. The 7-ply and 9-ply, due to their greater depth, obviously could span considerably more. But as you get into those, the cost reality starts becoming much more difficult. I mentioned briefly acoustics. Footfall acoustics, the IIC value is something that really struggles with CLT unless we start bringing in other elements to separate the mass from where the footfall is, or you start doing things underneath the CLT, which is something that you don't often see, because one of the attractions to CLT is it becomes your exposed ceiling. So as we start dropping suspended ceilings underneath it, it starts to question whether or not the added cost is worth it, not to mention having our structure be our finished product is definitely something positive. But the real big game changer is coming with IBC 2021, where the height of our structure due to fire is changing drastically, where the older IBC we're dealing with just type 4 heavy timber, where due to the study and the track record of mass timber products around the world, we're getting a lot of differentiation into what we can do, where you can see here, the current IBC is actually permitting us to go all the way up to 18 stories. And these are all taken for a commercial building in these particular studies. But as this density starts to improve, I think you're going to see the product become more and more attainable, especially like if you think of something like a residential building, only be able to go 6 stories with mass timber doesn't really give you that much benefit over stick framing. And as a result, you're not getting the bang for your buck. Really not comparable systems in terms of cost. CLT generally is getting compared more to steel and concrete systems when you're trying to think of cost and keep it on your project. And here's some more data on the fire separations. So one of the things I think you need to work with advocacy groups for where your projects are is trying to get the fire elements of IBC 2021 adopted earlier. And Colorado, we're getting those adopted, or at least in the city of Denver, we're getting those adopted early. And we're seeing different parts of the country, like the Pacific Northwest, where they have a significant vested interest in more timber. We're seeing that happen. We're seeing in places like Arkansas and even Florida, we're getting some better traction on getting 2021 adopted. So the real challenge, I think, with CLT is keeping it in the project and beating the value engineering, as I say. And the first step is and really this works for all structure, is think holistically. We need to be thinking not just about the structure, but the finishes, the acoustics, mechanical, what it means for the enclosure, the construction realities in terms of, is it going to be faster or slower? One of the natures of mass timber is it tends to be more of a panelized product and therefore is going to go in a lot faster. Say if you're comparing it to concrete, you don't have all the form work. Things of that nature have to be weighed in holistically as you're looking at the price and the appropriateness of the project. If you're just going to drop a ceiling in there, we're not saving the cost of a drop ceiling. Is it really worth it? How we integrate the mechanical systems, these are all critical. And once again, this seems to be true of everything, staying on module. Anytime we're going off module, it's going to be more expensive and more challenging. You know, Michael referred to maximizing our deck span. So if you have say a slab on metal deck that can go 10 feet, but you're only having your beam spaced at 8 feet, that's inherently wasteful of it. Same thing works with mass timber. So let's try to maximize our spans when we're using the material, and then also be kind of cognizant of what our manufacturer is producing them at. Unfortunately, there's not a uniform width that people are producing CLT at. It kind of ranges between 8 and 12 feet, although most commonly between 8 and 10 feet. This really starts to affect how you're looking at these floor slab systems in terms of your general module on your floors. If you're doing CLT walls, it becomes really critical. One of the things we've noticed with residential products, you want to take that CLT, instead of running it vertically, you want to be able to run it horizontally. If you only have an 8-foot CLT panel, your floor to ceiling is going to only be 8 feet, and that might not be a product that people are willing to buy. You might want to steer yourself to a CLT manufacturer that can go to 10. All of these things are critical, because what happens is when you buy that CLT, they're going to make it in what's most convenient for their shop, and then they're going to cut it down, and that's going to affect it. In terms of your carbon emissions, how they're managing that waste is always critical as well. Setting your grid based on what the mass timber does well, and that should be true of any material. You know, trying to take a steel grid and apply it to concrete, or a post-tension concrete grid and apply it to conventional reinforced concrete, all of them are not going to get you ideal results, and the same thing's true of timber. So working with the wood to accentuate its module early on is critical. Anytime you're dealing with glue lams that are supporting that CLT, elegance in the connections is critical. Oftentimes when we're dealing with heavy timber elements, the connections actually govern the size as much as the span, because there's only so much connectivity. The wood industry, people tend to just throw nails and screws at the problem, but more elegant connections, maybe using structural pins or simple bearing conditions, tend to be more efficient. And then hybrid systems can be used to, once again, like the king post, using steel where it's most appropriate, using the timber where it's most appropriate. And I already mentioned working closely with your manufacturers and engineers early as humanly possible to get the modules right. This is an example of a project we're looking at. We're during schematic design, we started investigating a lot of different modules, span and depth ratios of what made sense for this particular project. And this is going to vary project to project based on floor vibration requirements or live loads, but insisting that your design team investigate things in this manner, and then adding on to this what the embodied carbon content is for each of these systems, just like you'd review cost, I think should be the bare minimum you're expecting of your engineers. So just some imagery of what these systems look like. The most ideal system you usually see is the glue lam supporting CLT to keep as much mass timber in the project as possible. As we talked a little bit about the mechanical coordination, one of the tricks you see used every now and then is staggering the CLT and putting the mechanical in between the CLT, and then, of course, dropping the ceiling in to cover the mechanical, whether that be fire sprinkler systems or plumbing. This is something we're using right now on a project in Florida for an event center where we're running all the critical non-structural elements in the gaps. The challenge ends up being for your structural engineer dealing with his floor diaphragms to deal with his lateral loads, but that's a bit of your engineer's problem that can be done with something as simple as coil straps or even just sheathing over the top of the system.
Thanks, guys. We're going to have to start wrapping up here so we can answer some questions.
All right, I think that was it anyway. So thank you.
Awesome.
Sorry, didn't see the pop-up.
No worries. All right, so I'm going to share my screen really quickly. So I want to say thanks to everybody. There are a few more questions that maybe Chris, Michael, or Jeremy could chime in. We've got 2 more minutes or 5 more minutes. One of the questions was about functional units of concrete versus steel. Are there any good case studies that you could reference for folks to understand that? I know that was based on the one of the first slides that you had, Jeremy, but maybe Mike or Chris could also chime in.
Sure. Yeah, this is a tricky thing, and you know, people always ask, "What's the best material?" And of course, the answer is always going to be, "It depends." And I think one of the good things that Chris mentioned there, it's a real opportunity for innovation for both the architects and the engineers and the contractors and material suppliers. How do you optimize? And so there is no one single functional unit, right? You can compare you know, different designs for one ostensibly one application and come up with 3 solutions and hand it to a different firm, and they may come up with different solutions where another one's the bottom. So, but I think the good news is that's where the real opportunity for innovation is for a particular case, try to find the lowest embodied carbon solution.
Awesome. A few questions about wood. What's the best practice for treating end-of-life impacts with wood? Without them, there's a pervasive mathematical incentive to use more wood. Even when counting them, one could really be really rosy about the end of life, but ultimately not in our control. Anyone have anything on that one?
Well, there, I think really what you're looking to do is recycle the wood rather than just allowing it to go direct to waste to either decompose or burn. So reintegrating that in where they're able to make some of the engineered wood products that we're seeing is definitely the key on that.
That being said, there's another question in here about mass timber and engineered framing and how long the glue will last. Has anyone thought about that?
Yeah, I don't know if I have a firm answer on exactly how long the glue lasts, but there are glue laminated structures that have been around for like nearly 100 years. So it really is dependent, but I think that's something we can maybe get back with the audience on in more detail unless one of my colleagues already has a
Sunny, I'd like to just say something about timber. The Carbon Leadership Forum, the larger, not the local chapter, but the actual Carbon Leadership Forum, just hosted an 8-part series on timber, asking and attempting to answer all of these questions about you know, end of life, carbon sequestration, biomass, you know, the impact of the soil and holding the carbon, all of that kind of stuff. I would really encourage people to check that out. That's a great series, and I believe all of the videos are free online on the carbonleadershipforum.com.
I think that's a great segue. I'm sure there are many more questions. If you have them, please submit them. Myself, Caitlin, I think Mike even put his email on the Q&A. I wanted to thank our sponsors, but also our partners, and tell you that the next webinar will be on the envelope. It's next Monday from 3 to 4. And we hope that you'll all join us for that one, and look for the recording of this session, which will be shared with you via email later this week. Thanks again, Chris, Mike, and Jeremy. Really appreciate you speaking about each of these topics and sharing all the information that you have.
My pleasure.
Thank you.
Yeah, thank you, Sunny.
All right.